Welcome everyone to another JSO tutorial. In this tutorial, I'm gonna talk about factorization-free solvers, or start talking about it. Let's see how it goes. So essentially what I'm talking about is I'm looking at optimization, of course, as usual. And what I'm talking about is when you don't have the Hessian or the Jacobian explicitly of a problem. Okay, so this can include in some situations, in some contexts, for instance, LBF.js methods, and we're gonna see that I'm gonna include it as well here, except if you are factorizing the BFJS matrix. If you are using the BFJS matrix implicitly, then it applies to our factorization-free framework, okay? So the first thing we're gonna do is install some packages. So as usual, I'm using packages from JSO or JuliaSmoothOptimizers organization. And one of the main packages we're gonna use is LinearOperators. This package is gonna be used a lot implicitly, okay, especially when we use NLP models, but I'm gonna use it a little bit to explain what we're gonna do. The second main package is Krylov. So Krylov.jl, the package, is a repository of solvers for linear systems and linear least squares and least norm problems. So conjugate gradient being the most well-known, but of course you have other solvers in there, especially if you're looking into least squares. You have LSMR, LSLQ, MinRes, SimLQ. You have a lot of those, and a few that were released, developed a few, I believe, years ago, a couple of years at most. So you have cutting edge packages here as well. So these are the main packages. Let's start with those. So let's look at the simplest problem that I can explain, how a factorization-free solver is different from a solver using factorizations. So the first problem that we're gonna look is the simpler problem that I can use to explain is the minimization of a least square problem. The minimization of the residual of ax minus b. Okay, so here I have a m times n, b into the r m and x accordingly. Okay, so for instance, something like a equals ran 3, 10, 3, b equals ran 10. I'm gonna use random and random seed, and you want to solve the least squares problem of minimizing this residual. Okay, so this is a well-known problem. This is studied well before optimization, sometimes in the introduction to numerical methods. This is the data fitting problem, and the basics of this problem, the most simple way to solve it is to consider the gradient of it equals to 0, or you can look into a projection into the null space, which is also a great way of looking into this problem if you're more into linear algebra. So the solution to this problem is gonna satisfy this equation. A transpose AX equals A transpose B. So here, if you say A transpose A backslash A transpose B. You're gonna have the solution, and if you look at the residual, it should be the smallest possible residual, okay? Especially if you use linear algebra, should be a very small residual. I'm not gonna look into this problem in details. I'm gonna assume you have seen it before, and this means that this residual is in the null space of A transpose. So this is very small, okay? So this is the simplest way of solving this problem. Of course, here we have 3 variables. If you have 3,000 variables and a million rows, then this problem is going to be a little bit harder to solve. When we define this problem, we usually explain a few factorizations, or we use a few factorizations to solve it. The first one being the Cholesky factorization. So A transpose A is semi-positive definite, and if you have the columns of a linear independent, then A transpose A is positive definite, and you can use the Cholesky factorization. So here I'm gonna say that F is Cholesky of A transpose A. Okay. Remember that Cholesky is a function from linear algebra that computes the Cholesky factorization and returns an object of type Cholesky. And if you say F backslash A transpose B, you're using that factorization to solve this problem. So this is not the same as using the backslash here. This backslash here is specifically saying use the Cholesky factorization already computed, okay? So the thing is that in this factorization, you don't want to compute A transpose A, so you usually look into other factorizations. One factorization used in this problem is the QR factorization of A. So you can say F is QR of A. So I have these R here, which should be similar to this one, okay, except for the signs. And wait, sorry, here. And if you have A equals QR, where Q is a matrix with orthogonal columns, then you're gonna have QR transpose QR, X equals QR transpose B, and then this becomes R transpose R, X equals R transpose Q transpose B. Okay, so Q transpose Q becomes the identity of adequate size. So F dot R is RR, and you have F dot Q, which is actually a special object QR compact. From what I saw in the help, if you say matrix F dot Q, you're gonna have the aptly size F, and you can say F dot Q times B. I believe you can also say this, and it works as well. I'm not sure which one of these is faster. I think it stores f.q internally, so I'm sorry, I think it stores the thing, the queue with only 3 columns inside, so this may be faster. I'm not gonna benchmark this, I'm just gonna assume this is the one. So notice here that we have R transposed in both sides, and R is, as you can see here, non-singular. So these also become something simpler, which is Rx equals Q transpose B. So I'm gonna solve this as r backslash f dot r. And if you look at the solution, this is the same as what we had here. Okay, so this is solving the same problem. This is correct. So we're gonna look into this way of solving the problem instead of the Cholesky way, and compare it against the other way of solving it, which is by using a factorization-free variant, the conjugate gradient for least squares. And just so we don't have to do this again, I'm gonna say solve ls by QR a and b, and this is gonna be f equals QR of a, x equals f dot r, matrix fq transpose b. Okay, I don't need x equals. There you go. So let's look into the other way of solving it. So Krylov, as I said, is a package with a lot of solvers for linear systems and linear least squares and least norm problems. So the method that we're gonna use is CGLS, which is the conjugate gradient for least squares. So I'm looking to regularize linear least squares. I'm just gonna use zero regularization. And if you look into the normal equations here, you're gonna see that when lambda equals 0, that is actually what we have. So how do we run CGLS? You're gonna use A and B and optional parameters, which we're not gonna use. So that's it, CGLS AB. This solves exactly the same problem as we solved here with solve ls by QR. The difference being that you do not need the matrix. Okay, you do not need A, and this is a special part. Let's define a linear operator, OPA, which is going to be a linear operator of A. Okay, remember to look into my other video on linear operators for a full description of the package. So here when I say OPA equals linear operator of A, I'm wrapping A, in this case, to define a linear operator. And this CGLS method works the same way as if I had A explicitly, okay? So this, of course, does nothing to convince you about factorization-free solvers. What we're gonna do next is consider a more interesting situation, okay? So also let me just say a little bit about the output of this. So when I say CGLS, I receive two things. The first is X, the solution, and the second is QS, which is a Krylov stats object. It has a few information about the solution, in this case that it was solved, that it's not inconsistent, which are the residuals, the norm of the residuals, and the norm of the A transpose residuals. So notice that these go to 0. A difference also in iterative methods for linear systems or linear least squares is that you can pass a tolerance. So if you want a very crude solution, you can say something like r tau equals 10 to the minus 2. You're going to have a very crude solution, or you can be a little bit more You can be a little bit more demanding and say you want something 10 to the minus 12, for instance. Okay, so this is going to be very useful for the next parts of our tutorials, in which we're going to use linear least squares, or sometimes a quadratic problem, in the subproblem of our more general solver. And this means that we do not want a very precise solution. We just want a decrease in direction, essentially. More on that on the next tutorials. I'm gonna show you a simple example of a linear least square, which is gonna be made up, of course. I'm gonna create. I think I have to create something that does not blow up my computer, so I have to be a little bit unsure of the size of things. I'm gonna say I have a lot of points between 0 and 1. I'm gonna say random amount of points between 0 and 1. I'm gonna sort them for later plotting. By the way, I'm gonna use plots now as well. And what I'm gonna do is create fake data. I don't want something that is linear. I'm gonna create something with a sine wave. A bit of what I did here was I changed these to 100 and this a little bit to look a bit more with what I want. Okay, and so what we're gonna do next is I'm gonna feed this data, and then I'm gonna come back and increase this 10,000, this 100. So looking into this, I'm gonna try to fit this with a polynomial of degree 4. Let's see. So a polynomial of degree 4 here is gonna be xi to the power of j. So this is the matrix for the polynomial of degree 4, and y is simply y, so I'm not gonna redefine it. If I say beta equals solve by ls, solve ls by qr xy, I'm gonna have these arguments here, which given the size don't look right anyway. And I'm gonna scatter, or maybe they do because I'm in between 0 and 13. And I'm gonna scatter and plot x goes into beta 1 plus sum of x to the power of j times beta j plus 1. I'm actually gonna write j minus 1 for j equals 2 to the length of beta. And I'm gonna plot this between 0 and 1. Color red, line width 2. So yeah, it actually solved it a little kind of well. Let's assume this is a good value. Let's change this to 6. Yeah, that's fine. This is overfitted, of course. We're not worrying about that. We're just worried about solving a LS. So people from data science, please don't despair. So this beta equals solve ls by QR is not the only thing that's taking computer power. We also have to define x here. you could say, well, I need to define x, otherwise how am I gonna solve it? So this is what I'm gonna do. I'm gonna use a linear operator instead. For that, I'm gonna define two functions. I'm gonna define the function xprod beta, which is gonna receive a beta, and it's gonna output the equivalent operation. So this is taking each column and multiplying by a beta. So I'm gonna change this 6 to a value p. That'll be 6 here. As is usual in linear regression. So x prod beta and x transpose prod r. I'm gonna take each row. I'm not gonna sum the row. I'm gonna make a dot product of that row and a row, and that is this x to the power of j times r, and this is gonna be my output. Okay, I'm gonna define an operator of x, which is n by p plus 1, not symmetric, not Hermitian. It is real, and it's defined by x prod beta and x transpose prod r. So if I say OPX times beta minus x times beta, and I compute the norm, this is gonna be very small. I'm gonna define a r here. If I say OPX transpose r minus x transpose r, I also gonna have a very small value. Okay, so with these values I can use CGLS. Beta, so I'm gonna say beta 2 equals CGLS OPX and y, and here have it solved. I can compute the same things here. This can be changed to p plus 1. So this is our same thing, same way to solve a problem. Okay, and here I don't define the matrix, so I don't need the matrix. Of course, here I have an artificial way of defining this matrix. For the linear least squares problem, you're not going to have something like this, but it's a possibility. And this is interesting, especially in the multiple linear least square or the multiple regression, in which you don't have xij to the power of j. You have a lot of columns in which you make the mixed polynomial powers. So this p grows very fast. Okay. And what I'm going to do now is simulate a simulation like that, in which you have a lot of points and powers. Okay, so I'm actually going to make a new example. I'm going to leave this one behind, and I'm going to create an example here in which I have n and p given. For instance, 130. I'm going to create a matrix x and np, and n, I think it's more adequate. Y is gonna be x times a beta, so I'm gonna create a beta solution here. It's also gonna be random size p, and I'm gonna add a random noise. So this random noise is gonna be something like percent. Sorry. Okay. So I'm not gonna plot anything. Maybe to check that my solution is correct, I'm gonna use the norm of the residual. So for the solution, the actual solution, the norm of the residual is gonna be x times beta so minus y, and the norm of the residual projected into the null space. These are the values for the beta so. Notice that beta so is no longer the solution, is kind of far away. Maybe I can decrease this a little bit so it's not so evident. For 0 it's very small. For 0.1 is already very different. So let's keep it as 0.5. So if I say beta equals solve LS by QR of x and y, I'm gonna have I'm sorry, this should be beta. I'm gonna have the solution, okay? And if I do beta is CGLS and I take only the first argument, I'm also gonna have the solution with a lower tolerance, of course. Remember that I can change this to be a larger tolerance, but I don't want to, okay? Especially in regression, since you're gonna have overfit anyway if you do this to a very large value. Leave a comment if you think that you should have more precision than this amount of precision. These values are equal up to 4, 8, about 12 or 14 decimal places. Okay. So what I want to do is compare the time it takes to solve this, and the same way I'm computing the time, the number of memory that is needed. And I'm gonna show that as I increase this, I'm gonna have, they are obviously gonna both be slower, but my expectation is that CGLS is gonna be faster when I have a lot of a very large P or a lot of columns. So now I'm gonna increase this to 10,300. I have to run this a couple of times. And when I increase to 300, I'm gonna have 70 megabytes and 0.65 seconds compared to almost nothing and 0.007 seconds. If I have something a little larger, okay, so my computer froze a little bit and it looks like I'm out of sync with my voice. Really out of sync with my voice. I'm gonna solve this in post, hopefully. What we're seeing here is that when my P is large, or when I have many variables, I'm gonna have a lot of iterations, of course, in my CGLS. But since my products of x times beta and x transpose times r are kind of cheap in comparison to computing the QR factorization, the method is faster. Okay, so if I have a very large number of points and only 3 columns though, these will probably be faster to use QR. Okay, this is not enough, but if I have like a million, for instance, I start to see something Let's hope it doesn't break again. Well, if I have a sufficiently large problem and it's very simple to make a factorization. I also gonna have a lot of trouble if these X matrix, so if they are ill conditioned, that will also bring me trouble. So in this case, it's not happening. So this is great for my example. Okay. So this is it for the first part of a tutorial on factorization-free solvers. I'm gonna expand these on future tutorials to work on quadratic solvers and eventually work into a full constraint optimization solver. Take a look into my series on creating a solver. You can see that our working is progressing to that point in that series. So this will work well with that series. Okay. I hope you have enjoyed it. Please follow me on Twitch, on Twitter, and on YouTube for my latest videos. And thanks for watching. I'll see you next time.